Suppose that this is the sample cell. At rest, sodium ions are queued or lined up in the outer part of the cell, and potassium and the other protein ions that the cell membrane are not permeable to them are lying inside. This is the resting state. See? Resting. Electrocardiography is recording of electrical potential from the surface of the body that is coming into the surface of the body. In order to record the electrical potential, we need at least two electrons. The electrical current that is coming to the surface of the body is called electrocardiography. In 1842, if I can remember, an Italian physiologist can record electrical currents of the frog's heart from the surface of the body. Matteucci in 1842. "35 years later, Waller recorded electrocardiography of the human being from the surface of the body using 5 or 6 electrodes. Right leg, right hand, left hand, mouth and head. 35 years later. In 1901, a Dutch physician, Dr. Einthoven, removes 2 extra electrodes from the mouth and the head and the right leg. He noticed that these 2 electrodes didn't add more information and cross them out and use just right hand, left hand and left leg. 3 electrodes electrocardiography. In 1901. In 1924, he won the Nobel Prize for the electrocardiography discovery. Made a string galvanometer, because the electrical potential that has been produced in the heart are very weak. They cannot easily record them at that time. The electrodes were very big. Buckets filled with electrolytes. Cylindrical buckets with electrolytes. Put the right leg, left hand, the left leg inside it. So with big electrodes, you cannot record effectively. So he needed a galvanometer, a string galvanometer, which was very sensitive to very low amplitude charges, currents. That is why in 1924, Dr. Einthoven won the Nobel Prize for the discovery of electrocardiography. Let us see what is happening. Dr. William in 1934 up to 1938 add 3 more electrodes. I will discuss little by little. And during 1942, around a century, American Heart Association conferred electrocardiography and permits it to use in the clinic. The electrocardiography apparatus that was made by Dr. Einstein as 600 pounds and carried by 5 people. Very big. Just like IBM, the first computer that has been invented. As big as history. Now it is very small. The electrocardiography.
There isn't any cardiac clinic.
Yes, it is a portable one. And that can carry, those Chinese ones can carry with 2 fingers. Take a look. See what is the basic of electrocardiography. So we need electrodes, cables, amplifier, and a recording system to record electrical currents. Muscles and nerves can also send electrical currents, and you will have noises. You should emit those currents. Now, see what is happening. Suppose that this is a sample cardiac muscle cells. I want to record electrical currents of these sample muscle cells that is coming to the surface of the body. I need at least 2 electrodes. I put one here and one here. Connect them to a gauge. Am I right? To a gauge. Voltometer. Sensitive voltometer that is called a string galvanometer. If I put 2 electrodes at the surface of this cell, what can I record?
At the same surface?
At rest, yes. Is there any electrical potential between these 2 points? So when there is no electrical potential, I have a straight line. This is called 0 line. Isoelectric line in electrocardiography. And if I put it in pulse and a stimulus over the surface of the cell, then sodium channels will be open, sodium enters the cell. Here will be negative and here positive. And now, at this point, is there any electrical potential difference between here, this one, and this one?
Yes.
Yes. What do we call this stimulus? Depolarization. So, since you have dipole, negative, positive, this is called depolarization. There is a rule of thumb in electrocardiography. So now I have defined the polarity of electrodes. The polarity. So here is positive, here is positive, here is negative. Positive electrode, negative electrode. Remember, when depolarization approaches to the negative, this is negative, this is positive. Depolarization. When depolarization approaches to the positive polar electrode, you will have a positive deflection. When depolarization reaches to negative electrode, you have a negative deflection. Now depolarization starts from here, passes from negative pole to positive. At this time, you will have a positive deflection. At this time point, where do we have the peak depolarization value? When half of the surface of the cell, surface is depolarized. You will reach to the peak and then back to the isoelectric one. Means here and distant point. All the cell surface are depolarized. Means go to the peak, back to the zero line. Now all the cell membrane is depolarized. Depolarization starts from the S ring.
Yes.
Depolarizes both atria coming into the bifurcation
Of the ventricle.
till reaching to the first point in the ventricle. How much does it take? An impulse start from the SK node till reaches to the bifurcation.
0.2.
20 to the
0 point, no, till to the beginning of the ventricle.
0.25.
0.03 from the SA to internodal pathway. 0.09 in the AV. 0.03 plus 0.09, 1, 2 plus 0.04 in this one, 0.16. This is called conduction current. Did you get it? So at 0.16, the ventricle starts to be depolarized. Which part in the ventricle depolarizes first? See, this is the heart. Am I right? This is interventricular septum. The first part that is depolarized in the left ventricle, somewhere in the left ventricle, beneath the fibrous tissue, this part depolarizes from the left to the right. See, this is the negative pole and this is the positive pole. When depolarization approaches the positive pole, you will have the positive deflection. When depolarization move far away from the positive pole, then you will have negative deflection. In some recording, you will have a small negative wave which is called Q wave. Let's see what is happening. Here is depolarized. Depolarization then continues in interventricular septum to the apex and am I right?
So the Q is in the septum.
In the interventricular septum, somewhere beneath the fibrous tissue, from the left to the right.
That's in depolarization or repolarization?
Depolarization. Up to now, we are talking about depolarization.
But then why did it go under the 0 line?
Yes.
Why?
Which part? Q.
Q, yes.
See, when, based on what we have defined up to here, when depolarization approaches to the positive pole, we have a positive deflection. But here, when it moves far away from the positive pole, take a look, now it is moving far away the positive pole. Then we have a strong negative. See what is happening then. Depolarization of both ventricles after the first point start from the base to the apex. Means, take a look, means base to the apex. Closing, approaching to the positive or going far away from that. See, this is the positive, this is negative charge. Pole. See, from here to here. Approaching or going far away? Approaching. This is the positive, this is the negative. So then we will have a beat. Halfway, go to the beat. Then back to the 0 line. Now, the last part,
Doctor, R resembles repolarization.
we are talking about depolarization. Depolarization. Up to now, all the endocardial surfaces are depolarized. See? The last part of the ventricles that are depolarized, the last part, is somewhere here in the base of the left ventricle, where aortic artery passes over pulmonary artery. This part is called pulmonary cone. Pulmonary cone. Pulmonary cone. And the posterolateral base part of the right ventricle is the last part of both ventricles that is depolarized. Now take a look. See, now depolarization go up and then
Goes back to the base.
no, my question is that no, approaching the positive pole, going away from the positive pole. Again, you will have another negative deflection here. Now, all the ventricles are remaining depolarization state till depolarization starts. Are you hearing any question? So, this S wave signifies depolarization of the last part of the ventricle in the pulmonary cone and posterolateral wall of the base of the right ventricle. Now, in normal electrocardiography, we do not see atrial depolarization. See, atrial depolarized, remaining depolarization. After 1.6, we should see the atrial repolarization. Since there is less, there is no or less Purkinje fibers in the atria, repolarization is very slow in the atria. See, this is the atrial repolarization. Am I right? But before we can see the atrial repolarization, ventricular depolarization will be initiated. And then we cannot see atrial repolarization.
Because it joins with the QNS?
Yes, exactly. But if we have a special electrodes, we can record it.
So it joins with the QNS and
It is actually emitted in QRS complex. But now see what is happening. So we cannot see atrial repolarization or atrial T wave in normal electrocardiography. Now listen to me. In the atrium, the first part that is depolarized, where is it? SA. The first part that is depolarized is the first part that will be repolarized. Well, let us see what is happening in the ventricle. Where is the first point that is depolarized?
Atrioventricular septum.
Somewhere beneath the fibrous tissue in interventricular septum, which is depolarized from the left to the right. But since we have a high pressure inside the left and right ventricle, this is first. They have a delayed repolarization, longer repolarization. It means that the first part that is depolarized is not the first part that is repolarized. Means it is the last part that is repolarized. Due to high intraventricular pressure. So the first part is not the base. The first part that is repolarized is in the apex. So repolarization in the ventricle starts from the apex to the base. Take a look. Now here, at the end of depolarization are negative. Repolarization starts. See, they became positive. They start from the apex to the base. So, what is the duration of the T wave?
Up.
Up, exactly. Means depolarization and repolarization of the ventricles are in the same direction. Just the opposite case for the atrial tissue. Did you get it? Both depolarization and repolarization in the ventricles are in the same direction. See, at the end of depolarization, here are negative. The first part that is repolarized in the apex, here it becomes positive. Am I right? Repolarization, see again. Here the end is positive here. Take a look. Repolarization is the same direction of depolarization. So both depolarization and repolarization of the ventricle are in the same direction. Both have the positive wave.
It starts from the base waves.
Which one?
Depolarization.
Repolarization ventricle.
Yes.
From apex to base. From apex to
Depolarization.
Depolarization from base to apex. Repolarization is also from the apex to base. But what about the atria? Depolarization from here to here, from here to here. And they have in the opposite direction. Why? Because we have high blood pressure here. Since we have high blood pressure here, repolarization will have long duration. Inside the ventricle, we have high blood pressure. Just in the contrary, on the contrary, in the atria. Any question?
Do you mind if you could repeat it all, but in summarized, so we can connect it, connect the notes?
This is part of vectorial analysis. Up to here, I have make it very simple to learn. This is a sample cell. Address outside is positive, inside is negative. If I put two electrodes connected to a sensitive galvanometer, I do not record anything. I do not record anything. But when there is a stimulus, here we have depolarization, sodium enters. Now between these 2 points we have electrical potential. When there is no electrical potential, we have
Deadline.
isoelectric zero line. When there is electrical potential, based on the polarity, we will have a positive deflection or negative deflection. There is a rule of thumb in electrocardiography. When depolarization approaches the positive electrode, then we will have a positive deflection. So, depolarization initiates from here, reaches to mid part, reaches to the peak, then changes direction till it reaches to the zero line. This is atrial depolarization. Reaches to the bifurcation and into the ventricle. The first part that is depolarized in the ventricle is somewhere beneath the fibrous tissue of the valves from the left
To the right.
to right. From the left to right means in the opposite direction of depolarization. Then we will have a small cuvette in some leads. Leads means combination of electrodes, higher resistance.
There's 12 leads.
Lead. See, depolarization then passes in interventricular septum to the interior, to the endocardial part of both ventricles, still reaches here. The last part of the ventricle that is depolarized is somewhere in pulmonary cone and posterolateral wall of the base of right ventricle. Again, depolarization goes far away from the positive pole, and we will have a small S wave. Then all the endocardial surfaces and epicardial surfaces are depolarized. Straight line, isoelectric or zero. Now we want to start repolarization. Due to the high pressure inside the left ventricle, repolarization takes more time to start. So the first part that is depolarized is the last part that is depolarized. Means depolarization starts from the apex to the base. Now take a look. Here, the first point that is depolarized, the last point that is depolarized, the start depolarization. It becomes positive, positive, positive. It makes that depolarization and depolarization of the ventricle both are in the same direction. So we have a positive.
Where is the P wave?
P wave. This is the P wave. Where is your question is that where is the T wave of the atrium? It is actually
In the QRS.
behind the QRS, covers by the QRS complex. But if we have a special electrodes, we can even in normal electrocardiography we cannot see it. Even if we have electrodes, we can put it near any node. Mackenzie did it with Flack and Keith. In 1906, they have recorded the SA node depolarization and found that here is the SA node that can initiate the signal. The faster part of the heart that initiates signal is how did they get? By recording the SA node depolarization and repolarization. Mackenzie, Flack and Keith in 1906.
Doctor, which lead would this be?
Pardon?
Which lead?
Which?
This one, yeah.
What do you mean?
Which
lead?
Yes.
I will discuss the combination of it right now. Suppose that we are Dr. Einthoven and we want to record. See what is happening during Einthoven. In 1901, Einthoven introduced 3 electrodes, electrocardiography into the science. As I told you, the electrodes were very big at that time. Bucket, a cylinder filled with sodium chloride. Put the right leg, left leg, right hand and left hand inside the buckets filled with electrolytes. You want 2 electrodes, see? Right hand and left hand, the electrical potential. that is coming to the right and left hand from the heart to the surface of the body. This is called limb lead 1, bipolar, 2 electrodes, 1 between right hand and left leg, limb lead 2, 1 between left hand and left leg, limb lead 3. Right leg is the neutral electrode in normal electrode. Connect the cable to the right leg and attaches it, connect it to the earth. When you walk, you have a static electricity, which are waste currents or noises. In order to cross them out, Dr. Einthoven, because recording is very time-consuming and intricate process, you need a special cages. Very cumbersome, very difficult. I have done this. Very difficult to learn and practice. So that is why Dr. Einthoven invented a string galvanometer. If you go through what he did, you can understand how difficult it was during that time. So connect the right leg to the earth in order to cross out the static currents. So right hand, left hand, right hand, left leg, left hand, left leg. See, Dr. Einthoven was a very good and professional mathematician. By connecting the lines between right hand, left hand, right hand, left leg, left hand, left leg, he invented a triangle, an equilateral triangle, which is now named after his name, Einthoven triangle. Equilateral triangle. Right hand, left hand. Right hand, left leg. Left hand, left leg. Equilateral. How much is the angle? 60. 60. Exactly. Let me transfer these lines to the center. This is limit 1, limit 2, limit 3. Am I right? Yes. Limit 1, limit 2, 1, 2, 3.
Why, on what basis did we all agree that this is 1, 2, and 3? Like this?
See, this is between right hand and left hand.
Yes.
Transfer this one here. See, this is limit 1. Transfer here. So
they
if we move from
So they all start from top.
yes. See, suppose that we move from limit 1. Limit 1 equals to 0 degree. How much is the limit to? 60? 60, exactly. 60. 60 degree. What about limit 3?
120.
120. Exactly. In 1901. See, Dr. Wilson at 1934 thought that in electrocardiogram we need some electrical information between 0 and 60 and 120. There was something between these angles. The electrodes very weak at that time. Doctor gives